Okay, we're officially recording. So today we're going to talk about looping statements in Small Basic. Next week we're going to get into Python and how Python interacts with our software. The first thing I'm going to do is, I don't have a lot of presentations here, so what I was going to do is talk about a few different programs, the way that I solve them, and then we are going to actually just start looking at the homework, to be honest with you, and look at solutions to get to talk about the homework. So after my little spiel here on these, but the first thing we're going to look at here is some of the programs that we were talking about with the quadratic formula. Now, first of all, what is the quadratic formula? Tell me why, what is it? Why do we need the quadratic formula? What purpose does it really solve? Was it just another thing you had to memorize in math class? What is it? What is it to you? What is it to you, Michael? You remember the quadratic formula? Okay, what's so important about that? Application. Okay, good. All right. So Michael said negative b plus or minus the square root of b squared minus 4ac over 2a. So what's so okay? So what's equal to that? No, this is x. So if we have something that says ax squared plus bx plus c equals 0, we can solve x using this formula, right? So we have, if it's in this form, we can solve x using this formula. And they go and solve for x and do all this other kind of garbage shit. Remember all that factoring, like x squared minus 16x plus 4x minus 4 and all that other stuff you had to do. Basically, this does algebra 2 for you right here. This does all that factoring. Because what is a factor? When we do factoring in math class, what's the whole goal? What's a factor? Why did you factor? Why'd you spend all of like 10th grade doing all this stuff? How about here? Why'd you spend all 10th grade factoring? What does factoring mean? What's the actual word factoring mean? I have something like x squared minus x minus 12 equals 0. How do I factor this thing? X squared minus x minus 12 equals 0. It's been a while, huh? You think this is like, remember this? You remember it, you just don't know how to do it. We do a little, x minus 4, x plus 3 equals 0, right? Does that ring a bell? Oh, good. Ariel nodded her head. So if we know this times this equals 0, we know that either x minus 4 is equal to 0 or x plus 3 equals 0, right? If two numbers times each other equals 0, one of them's got to be 0, right? And so we can do the little, x equals 4, x equals negative 3. I used to teach math in a prior life, probably before most of you were even alive. So 4 or negative 3. If we plug the little 4 back in here, we can see it works. We plug the negative 3 back in there, it works. Now, these are nice, pretty numbers that I know is going to work. Now, we put in these numbers right here. Now, here, a is equal to 1, b is equal to negative 1, c is equal to negative 12. And if you were to plug these numbers in here, you're going to get these. Now, it's not going to look nice and neat like this all the time, right? Okay. If I had something like x squared Can we think of numbers, multiples of 27 that add up to negative 27 that add up to 1? We got 1, 27, 9, and 3, and that's it. So you're gonna get really wacky stuff when we plug it into here. You know, we're not gonna have these nice perfect squares that come out here. So most of the time, we're gonna get numbers that have really odd things here. Now, the other problem that we run into is, what if we get a number like A is equal to 1, B is equal to 0, C is equal to, say, 4, okay? Well, we're looking at something like x squared plus 4 equals 0. Can you solve for x? What's x equal to here? 2, well, maybe 2. You got into imaginary numbers. We don't like imaginary numbers. What's that mean? You know, we can say x squared equals negative 4. Can I think of any number squared that's going to be negative? No, negative times negative equals positive. Positive times positive equals positive. And so what this thing does, and you can go, if you really wanted to spend your life doing this, you could go and solve for x and get all this stuff. So what we did here was we did this quadratic formula. And like Andy pointed out, we've got these things going on here with this formula. We've got this square root sign. Now, what's the square root sign do? Can you tell me in words, what's a square root? It's getting real ugly real quickly. At least everyone's making eye contact with me. We got some people just stare to the back. They don't. Helps to balance an equation. Whatever number times itself is square root. So the square root of 9 is equal to 3. Was there another square root of 9? Just 3? What else? What about negative 3? Negative 3 equal to 3? 9? So in some cases, it's going to have 2 square roots here. And so this part here is what we call the discriminant. Does this kind of ring a bell from math class a little bit? I remember. Big fancy words here in math class. So this thing's called the discriminant, negative b, plus or minus. So basically, there's 2 separate equations here. Because when we have something that's x squared plus 4 is equal to 0, not in this case here, but something like x squared minus x minus 12, does anyone know the equation for what this looks like? If I were to graph this thing, and those of you who've taken geostats with us, remember that equation y equals mx plus b. What is this the equation? Y equals mx plus b from our regression. What is this the equation of? Straight line. Okay, this thing is a parabola, some sort of curvy thing there. Okay, and basically where x is equal to 0 is where it intersects the x-axis. Okay, and if it doesn't intersect the x-axis, then that's where we get into that stuff like this, but we don't worry about that. Those are those roots right there. So we've got this formula right here. So we got this thing called the discriminant here. Now, in a computer, if you try taking the square root of something that's negative, what's it going to do? Really bad things, because when I ran the program, I had this like red stop sign come up when I ran it in this. And this is the last question that we talked about this is the last question on the homework. And so when I kind of think about it logically here, do I need this here, or I'm going to get rid of this? Is this okay? So when I think about it here, what's the first thing we're going to do? Okay. So I write this program to figure out the quadratic formula. What's the first thing you do? Give me A, B, and C. Okay. A, B, and C. What are those things called here? Like 2x minus 2x squared minus 2x minus 24 equals 0. What is this 2, and 24? What are those things called? Starts with a C, another long word. Coefficients. So these are our coefficients right here. So a lot of times if you have an equation that's something like 2x squared minus 2x equals x plus 3. Well, guess what you got to do? You got to move everything to one side, and then you got your A, B, and C. Okay, you guys didn't think this would be a math class, huh? Okay. So the first thing we got to do is, and this is the little program that I wrote here. The first thing that I said is, hey, we got to put up a prompt using a right for A, B, and C so that we can get the coefficients. So the very first thing is we get A, B, and C. Very first thing. Does it matter if they're positive or negative? Does it matter if A, B, and C are positive or negative? It's going to be negative 17. Okay, do I need to do any checks to make sure they're right numbers or correct numbers? I can if I wanted to. If I typed in a Q, it wouldn't yell at me, but look what I have there. I have that read number. So if I type in a Q, what's it going to assume it to be? 0. And so if we really wanted to, we could put these checks in here. But is there any stipulations as to what the coefficients are going to be? No, as long as they're real numbers. I could put in negative 1.7, 83.6, 5/6, or whatever I want to do. It's just going to make this factoring a lot uglier. So first thing we're going to do is ask for A, and then we're going to use that read number. What's this command read number do? I've got this command here, read number. What's it do? Store it. Okay, and I have something here. The first line says text window dot write, please enter A. What do you think I'm doing? You're just printing out, please enter A. And the next question says A equals text number dot read number. And you notice the parentheses there. Okay, these are what we call input parameters. And Small Basic uses the term arguments. You notice that you ever see that term when it had an error, arguments? Hey, what's going on in the parentheses? You got nothing, there should be nothing, there should be something. And so when I do the write, it needs something. How many somethings does it need? 1. If you put more than one thing there, okay, it's going to yell at you. Okay, separate it by commas. If you add a plus sign to it, it's going to work. And so A is the variable. Okay. Equal to sign in computer programming language, what does the equal to sign mean? It doesn't mean equal to. A sign. We're signing it. My dad always said takes on the value. So we've got some variable called A called takes on the value of whatever you type in. Read number. Do we have to call it A? No. Why did I call it A? Because it's part of the ax squared plus bx plus c equals 0. It's easy for me to remember. We're going to talk about a couple of these programs too. Next thing, all I do is cut and paste, and I call the next variable B, I call the next variable C. And so now I've got this A, B, and C. Now the next thing that I did was I used the right line, or the right in this case. The difference between a right line and a right line just goes down a line and hits an enter, while that right means it's going to keep it on the same line. So I did that. The next thing that I did was I calculated that discriminant, that whole thing under the square root, which is b squared minus 4ac. Because really major thing, we got to have 3 different things happen with this discriminant. If this is negative, so if I go and calculate this to be like negative 20, what's going to happen here? You can't run this. I did it before, and basically it said, this big red thing came up and said, sorry, I can't run this because you've got a negative square root. We're dealing with, what are they called? Imaginary numbers or not real numbers or whatever. Okay? The other thing that can happen is, what happens if the square root is equal to 0? Close. What's the square root of 0? What times itself equals 0? 0. That's okay. Okay, but that's going to be a special situation too. And then the next, we get something like the square root of 14, or let's get something better, even 60. So that plus or minus is part of the equation, not because someone went and figured it out, is because, well, what are the square roots of 16? 4, or what else? -4. That's where we get the plus or minus from. And so we've got 3 different scenarios here. And you can see I have this if statement. Now I was talking, I think it was Michael before, about the if statement. So I went and calculated this discriminant that says b times b minus 4 times a times c. Why do I have those parentheses right there? This is my order of operations right there. I didn't want to I just wanted to do the b squared, subtract the 4ac. Why didn't I take the square root of it right there?
Because it could bring up an error.
It end up in error, exactly, Andy, yes. Because the first time I did it, I calculated the square root. I just said this discriminant, I don't care if it's 20, 8, 0, -20 or whatever. I just know if it's below 0, I'm going to get garbage. If it's 0, that's going to be another situation. If it's above 0, if it's greater than 0, I'm going to have another scenario. So the 3 possible situations that I can have for this discriminant are they're less than 0, they're 0, or they're greater than 0. So all I'm going to do is run an if-then-else statement. Now, we ran a couple of if statements here, and I'll talk about a couple of these here in a second. And so, okay, let's figure out this discriminant. Okay, figure out discriminant. Yeah, math is so difficult because it has these big, long words, too. Okay, so we get X, Y, and Z. And we can do error checking and all that other stuff later, meaning, hey, did you type in a Q? You typed in a Q, go back again. We're not going to run that because I have that read number there. And so it's going to assume you put in a number. If you were dumb enough to type in a character, something is just going to say, I'm not dealing with you. I'm going to make it 0. We're going to move on with our lives. Okay, so what are the 3 situations that we have? Okay, if this discriminant is negative, what's the first thing that I did? If discriminant is less than 0, why did I call that variable discriminant? Because when I go back later, it's called discriminant. So the one thing we need to differentiate is that this is a variable name, takes on the value of b squared minus 4ac. I called it discriminant. There might be a variable out there called like right line. You can't call stuff like cosine because, well, cosine is already a variable. And so even these very simple programming language are going to start to yell at you if you break laws of like mathematics, real numbers, as well as you start naming things like end if. If you want to name a variable end if, it's going to get mad at you. And you notice how it's in blue. You start to see these things in blue here. These are going to be statements or commands that the computer software understands. And then you see the text window .write. So those are basically what we call objects right there. I didn't go and make those pretty colors. Computer went and did because it knows exactly what those things mean. And so we have some what we call decision structures, and we're going to talk a little bit more about those later. But it says if the discriminant is less than 0, what are we going to do? We're just going to, the roots of this equation are not real. Now this is if, else, else, meaning you can have this, or you can have this, or you can have this. You can't have any of the other 3s. And this basically treats it like an exclusive OR. Does anyone remember that term exclusive OR from GIS a long time ago? It could be one or the other or the other. In this case, it's not one or the other, but one of 3 others, or one of 3 scenarios. There's no way the discriminant can be less than 20, less than 0, 0, or greater than 0 at the same time. It could be -0.1, it's still less than 1. And so it says the roots of this equation are not real, goodbye. It just says, kicks you out. What's the next situation that we have? Else if, meaning, all right, if it's less than 0, I perform this command and I get out. The next situation, else if the discriminant is equal to 0. Okay, so now if it's negative, we just go by. Next, if it's equal to 0, Now let's go back to this equation here. Negative b plus or minus the square root of b squared minus 4ac. Let me write it up here, because I want to make sure everyone here joining me. So x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Now, if this discriminant is 0, what's the square root of 0? 0. And so now it's just going to be negative b over 2a. And that's what we call a double root. Has anyone heard that term before, double root? So now, when we look at this situation here with this else if, and I'm going to highlight this for people here. Else if, we're looking at this one here. Else if the discriminant is equal to 0, the root is equal to negative b times 1, all divided by 2 times a. And I kind of keep those order of operations together. You notice I put those in parentheses, right? Because in theory, division and multiplication are kind of the same thing. And so I get scared if I don't put the division sign here. I get rid of the parentheses. It's just going to run this equation across, when in reality I want to do the numerator and then I want to do the denominator. Okay? So I've got that. I haven't even done anything with, the funny thing is I haven't done anything with the square root yet. I talk all this whole time about the square root stuff. I haven't even utilized the math function for square root. Haven't even utilized it yet. And so, okay, next. This equation has a double root, and the root is root. Okay, I just called it root. So root is going to be, it's going to be basically listed twice. Okay, so if you have something like x squared plus 9. Oh, that would be good. I'll think of one here in a second. Something like x squared plus 2x plus 6x plus 9 equals 0. So we got x plus 3, x plus 3, x is equal to negative 3. And so if I were to do b squared minus 4ac, 36 minus 4 times 9 times 1, 36 minus 36 equals 0. So this would be an example of a double root right here. Hopefully this is all coming back. I'm sure it is. Okay, so else if, this is called the double root. And so in that case, the double root is going to be equal to negative 3. They're both equal to negative 3. Still haven't run square root yet. And so x is equal to, what is it, negative b over 2a. That's pretty simple. Last thing, all right, this is where we bust out our math right here. And so the very last possibility that we have is that, why don't I put the word else? Because you notice else if has the discriminant equal 0. Else is, that's everything else that didn't satisfy the first part or the second part. There's only 3 different possibilities. 3 different possibilities. So now else, all it is got to be greater than 0 because we've exhausted all the other possibilities. Okay, and so root 1 is equal to negative 1 times b times math dot square root. This is just the function for math. So math dot square root of the discriminant all over 2a. And then what did I do for the next one? Plus or minus. That's all I did. So one root is the plus, one root is the minus. And all I did was just write it out the same way. Okay, a couple things you notice here. Why do I have 2 parentheses here? Why do I have 2 parentheses around this? I only have 1 up there, but why do I have 2 there? I've got 1 parenthesis here, 1 parenthesis here, and I'll point this out for people online too. Okay, I'm looking at the root 1 and root 2 right here. Why do I have 2 parentheses here, but only 1 parenthesis here? Any ideas? What are you saying, Andy? Have any ideas?
I'm trying to group the numerators together.
Exactly. I want to group this numerator together. That's the whole goal here. I want to group this numerator together. And that numerator is negative b plus the square root of the discriminant. Okay, because I went through and already calculated the b squared minus 4ac up at the top. So the square root of the discriminant all divided by 2 times a. And so this is in one parentheses here. This is in another parentheses there. Okay. So that, because I can't just do the big division sign here, I just divide it by that. And next, I just use the little text window that says the roots are root 1, root 2. So who did this one? Did anyone solve this one for the homework? Is this how you did it?
Yeah, but I didn't do the LC.
You didn't do the what?
The LC.
Oh, the LCIFs? Okay, you just did 3 separate if statements, right?
Yeah, two separate. So I did if discriminant is less than equal to 0. Like, it's 0.
Okay, good. And those of you joining, Chima said he did 2 if statements, right? And then one of the if statements said if it's less than 0, then it'll just, if it's less than 0, then it does something, right? It gets rid of the program.
So if it's less than 0, it gets rid of the program.
Yep.
If it's greater than or equal to 0, it runs.
Exactly. And if it's greater than or equal to 0, it'll run this thing, because what happens here when you have the discriminant, if both of these things are the same, if both of these are 0, this discriminant is 0, negative b plus 0 over 2a, negative b minus 0 over 2a, they're the same thing. They're the same exact thing. But he did 2 if statements, because what are the only possibilities you could have? Less than 0 or greater than or equal to 0. I can't think of any other numbers out there that exist that are neither less than 0 or greater than or equal to 0. So he's got everything covered. And he used if statements. He used a couple of if statements that are perfectly fine. Okay. Me, it just said it's only got to be one of these 3 possibilities. Only one of these 3 possibilities. So this was, the second part of the homework. Feel free to use these or do whatever you want with these, because we're going to look at another one here. We're going to talk about these while examples here, get an idea of what we're looking at here. You notice here I did one conversion one right here, enter the temperature, read number. Did we have to do a conversion one for homework? Okay. And I think I had you also do Kelvin or something like that. Kelvin, Fahrenheit, and Celsius. So this is a little bit different, but Celsius is equal to Fahrenheit minus 32 divided by 1.8. What's the whole goal of Celsius? Why do they make up this extra Celsius stuff if we don't, I don't even know it. I always hate it when people are like, it's really warm out, it's 30 degrees out. I'm like, no, it's not warm. But warm is it's like, in the 80s there, so when you go overseas or go to Europe, it's like, no, 30 isn't warm. I'm like, yeah, it's really warm. Because I know, Chima, you'll talk about Celsius. Now, what's another scale for Celsius? What else do they call it? Centigrade. Why do they call it centigrade? It's based on a metric scale, so that freezing is 0 and boiling is 100. Here, what's boiling in Fahrenheit? 212. What's freezing? 32. 32, exactly. We got 0 and 100. And so basically it's just some sort of it's a linear conversion between the two, so they can equate those. And so once at the end I did read, and then I just did a right line that converts these things. So I like this one, because what we're going to talk about today, I'll talk a little bit and then we'll just kind of get into the homework, is we're going to do these things called for loops. And Benjamin was here the other day talking about, we want to kind of start to automate processes, right? I want to keep doing these things over and over, because I don't think I have it here, but I've created a pretty neat guessing game, being guess the number between 1 and 100. How many times is it going to take you to do that? Might be 1, might be 3, might be 5. Who knows? I don't know. So some of the things that we can do is we can start to automate processes right here. Now, here's a real simple one that says for x equals 1 to 50, it says text window dot right, the number is x, and then N4. I kept typing in like next x because that used to be the old command for basic here, but when I run this thing, let's see what it gives me. I run this thing. Look what it does. It just goes here, the first line, 1 to 50. Press any key to continue. And so you'll see a couple of the other things here that I've got here. I got this neat one here, quadratic formula, Pythagorean triples. Let me see. Now, this is a real neat one with some for loops here, but what's a Pythagorean triple? This is from the homework here. What's a Pythagorean formula?
C squared equals.
C squared equals a squared plus b squared. There's a derivation of the law of cosines, which is c squared equals a squared plus b squared minus 2ab cosine c. But what's the cosine of 90 degrees? 0. 0. So it's just c squared equals a squared plus b squared. Remember the law of sines and cosines? A little bit. A little bit there. That's okay. So we got Pythagorean triples. Those are numbers. Those are whole numbers that satisfy a squared plus b squared equals c squared. And I'm going to show this neat little formula right here, this neat little program I wrote, and then maybe you can work backwards for this thing because you get an idea. This has got some nested loops and all these weird things in there. And you can see Pythagorean triples and we see powers. We raise things to powers. What's a power? X to the second power is x times x. 5 to the third power is 5 times 5 times 5. And so numbers like 3, 4, and 5, if we were to raise these to the second power, 3 squared plus 4 squared equals 5 squared. Right? So what are some other Pythagorean triples out there? Oh, some of these are real hard, huh? What about 6, 8, 12? Or 6, 8, 10? Do you think every multiple of 3, 4, 5 is going to be a Pythagorean triple? No. Then we got some other weird ones out there like 5, 12, 13. So 25 plus 144 equals 169. Doesn't someone want to know all the Pythagorean triples? Andy's just shaking his head like, no, I don't want to know those. No. So I created a little program that kind of does this here. I thought this was kind of neat. But you can start to see all the Pythagorean triples. And look how long it takes to run. You can see 3, 4, 5. And I had these hypotenuses going up to 500. Because when we do these calculations, what do you think it's doing? Is it just picking out 3, 4, 5, or is it trying, let me try 1, 1, 1, and then 1, 1, 2, and then 1, 1, 3, and then 1, 1, 4. How many of those calculations do you think we're running? A lot. And so now when we're getting down to like 425, 430, 51, 432, 232, and 438, this is what we get. And so these are some of the Pythagorean triples that have a hypotenuse of less than 500. It's pretty cool. Now, I don't think I'm going to make anyone in this class do that. Don't worry, Barbara. Definitely not. All right. So you can see some like, did anyone look at the 132, 475, 493 Pythagorean triple? That's pretty cool. Now, this is probably, I don't know what that one is. 12, 4, I don't know. But these are all Pythagorean triples whose hypotenuse is less than. Now, how long do you think it would have taken me to do something like this, or you calculate these by hand? Well, forever, a long time. And even in small basic, these things took a while here. But you can see some examples like 7, 24, 25, and then obviously some of those multiples of 3, 4, 5. So 3, 6, 8, 10, 9, 12, 15, 12, 16, 20, 15, 20, 25. Those are all Pythagorean triples. And then you kind of throw in some of these weird ones like 11, 60, 61, 9, 40, 41, and then the multiples of those. But how we automated this was using these things called loops. There's 2 different types of loops that we'll talk about today. One's called the for loop, one's called the while loop. So a for loop is going to kind of be dedicated to something like this, where I write a number and it's going to print out however many times that it says right here. So for x equals 1 to 50, and it says text window dot write, the number is x. Now, if you wanted to, you could type in the number like, hey, how many numbers do you want to print? Because what you're going to be doing for homework is you're going to be printing out like times tables. Like 6 times 3 equals 18. 7 times 3 equals 21. 8 times 3 equals 24. And so we're just going to be doing a little bit of multiplication, probably writing 4 or 5 lines that do this so that you can do the times tables for my kids when we start doing them. Okay, so you can do the 1s and the 2s and the 3s and the 4s or whatever we're trying to do here. So we got a for loop here. The last thing I'm going to kind of mention before my little talk, and then we'll kind of just start talking about the homework, is something called the while loop here. Okay, now I want to go and calculate your test scores. I want to calculate the average for all the test scores. How many am I going to calculate for this class? Oh, 22. How many for my other class? Not 22. And so you can see what I have here. I have a text window dot write line that says enter a number or enter a score. It says type -1 to n. And so we're going to enter a loop, and it's going to keep 2 in this loop, and it's a conditional loop. What's a condition? It's like an if statement. It's just an if statement. Okay. Now, previously we looked at that conditional loop. We looked at that for loop. It just went through however many times it was in the 1 to whatever. Now, 1, it doesn't have to start at 1. We can start at 2 or 20 or 27, or we can count backwards, to be honest with you. And those things are called steps. So it doesn't necessarily have to start at 1, or you don't necessarily have to count by 1. And so there's neat ways that you can kind of append that for loop in order to do this. So this says while score, and then the next line says score equals text window dot write number. So read number. So what am I doing? When I write the word read number, what are you as a programmer doing? Not me. What are you doing when you write this? You're asking the user to type something in. That's all you're doing. Now these are different types of input and output we can do. While I'm thinking of it, I'll show another program that I have here where that input is going to be slightly different. And so you're going to type in a number, it's called score, and then we're going to enter a loop that says while score. What does that symbol mean? What does this stuff mean? Wait a minute, it does not equal. Does not equal. And so this symbol here, okay, and we're looking at this one here, okay, and we're looking at this comment right here. This means does not equal to in small basic. Now, in other languages, you'll see something like equal to with a little exclamation point. So those of you who've done raster class, in raster calculator, I think it's that's does not equal to. And so this says, while num does not equal the -1, and then what are we going to say? The number of scores equals the number of scores plus 1. Basically meaning, when I calculate the average of something, how do I calculate the average of your tests in this class? What do? I got to add up all your scores and divide what? By the total number of scores that I've taken. And so you can see, if you kind of look ahead here, I calculated an average, and I'm calculating the average of your test score. So the first thing I said is the number of scores equals the number of scores plus 1, because at some point in time, I'm going to need to do a calculation that says the average equals the sum of all your scores divided by the total number of scores. Now, I don't want to waste everyone's time and call this variable total number of scores, so I just said num scores equals num scores plus 1.
You write in small basic, instead of writing num scores equals num scores plus 1, then you write num scores plus equals.
I don't think so. Okay. Shiva's got a good question here, because in Python and other languages, you can say num scores plus equals 1 instead of me having to write that again. So what are we doing here? We say num scores equals num scores plus mun, basically meaning whatever num scores was, add a number to it. So if it's 23, what's it going to be next? 24. Now, when we start the program, what is the num scores equal to? 0. And if I really wanted to up at the top before I put score, I could probably put num scores equals 0. But if you assign a random variable, it's always going to take on the value of 0 to begin with. So I've got this variable called num scores. I got this value called score. I got this thing here called sum. So I got a bunch of different things going on here. And eventually I'm going to have this thing called average, this variable called average. So I've got 4 different variables going on right now that I need to make sure they're correct. Same thing with the A, B, and C. You know, because I went through and ran my discriminant program and I missed the parentheses and it calculated them all wrong. And so getting a good idea as to what a good answer is going to look like. If I type in 50, 100, 50, 100, the average better be 75 and the number scored better be 4. If not, you made a problem with your calculation. So num scores equals num scores plus 1. The sum equals the score plus the sum. So the same thing that Chima alluded to before is the sum is going to be whatever the sum was. So if you have 2 scores that added up to 180, I have 100 now. So I'm just going to do 180 plus 100. So I could do sum plus equals score. But I'm just going to say sum equals score plus sum because I don't think that is going to be working in small basic. And then next I'm going to say, hey, while I'm in the loop, type in a number again. Write number one, type -1 to end, and then it's going to read in a score. And then it's going to run it again, run it again, run it again. Now, what's the only way to get out of this loop? Type in -1. That's the only way to type it in this loop. And we're going to show an example of what happens if you don't. Because the only way to get out of this loop is to type in, because when I ran this the first time, I didn't have this line. So what do you think is going to happen? I don't have this line. What's going to happen? The user's not going to know how to get out of it. Now let's see what happens here. So I'm going to run it. I'm going to type in, all right, I got a 90 here. It just keeps running. Why? Because the user doesn't know how to get out of the loop. So this while loop, okay? There's other variations of these, so we can look for some of these while loops. So this loop is going to run while that condition is true, okay? The only way to get out of this loop is to type in -1, not -1.1, okay? So we're going to go back here. So now I'm going to run this thing. So I'm going to type in, a 90, an 85, an 80. And then we'll take them to -1. So before I even run this, what is the average going to be? 85. What's the number scores going to be? 3. So before I even run this, I should know what the right answer looks like. So the average of the 3 tests is 85. And so the last thing that I did here was I calculated the average, which is the sum, because within this loop, I go through and average everything up. And then the average of the plus num scores, what does that plus do again? I've got this plus right here. And what's this plus do? Concatenate. Because remember, what are the number of arguments? When I do the right line, what is the number of arguments that you can have? 1. Exactly. And so you need this here because watch, if I don't put that there, it's going to say, hey, you supplied 2 arguments, but it only takes 1. Now, or something like this. I run something like this, it's going to say, hey, it takes 0 arguments. I don't know why you're putting anything in here. It doesn't take anything. Okay. Previously, I think when we get into Python, they're going to use the term parameters, input parameters. But these input parameters will be numbers or whatever that we can generate. Okay, this input is just stuff that we type in. And so now let me run it again, just for the heck of it. Watch what I do here. I'm just gonna type in -1. The average of the blank test is 0. It's just, it never even went through the trouble of opening the loop. Okay, so if it was really silly, I was being really silly, I went and typed in -1 to begin with, and it just exited the loop. So there's gonna be different variations of those as well. So I really like kind of those things there. I thought I had another neat thing here, guessing game, my program, conversion for, this is the guessing game that I created. I thought this was pretty neat. But you notice what I've got like here, if I've got some while loops. Oh, wow. And you can see kind of what I did again here. This is a guessing game that I created. So 50, too high, 25, 12, 17, too low, 20, 22. You guessed too high. Oh, 21. You guessed it correctly in 7 numbers. So once again, if you kind of look at this guessing game, guess a number between 1 and 100 or whatever. You can see I created a random number generator. Okay, so that math library creates random number, but look what I did. I happened to pick a number, and then that's what I got right here. So I've got a while loop right there. I created a while loop. Over, I created a variable called over, which basically means game over. So 1 means true or whatever here. I thought I had some neat little program here that I had. I swear I did something really cool here, but we'll see here in a second. Oh, here it is. Draw circles. Oops, okay. I don't think people want to hear oops. All right, so we have data handlers. Week 3. All right, I got this neat thing here. So we do have different types of handles here, because what has been the input that we've typed in, used thus far? You just typing in a number, hitting enter. And so I started to handle, I created a couple little programs that have, what they have, event handlers. What are the different events that you can handle where basically the mouse is down? And then here's a neat one here where that on mouse down, I create. So now I can do this. I just created, like, just in a few lines of code, this little program right here. There we go. And so now I've got these different things that we can do here. Brush color equals blue. What do you think that means? Well, brush color equals blue. So the one thing that I kind of encourage people when they do research or do anything, you've got a program that works. What can you do? I can go and change some of these numbers. Oh, what do you think this is going to do? Pretty cool. I don't even know what this did. What did I just do?
Based off of where you click it at.
Exactly. So it moved over from where I clicked it at. And so I assume that 10 was because it was in the middle right there. So looks like it has 4 different input parameters. It's got an X, it's got a Y, and then it looks like this is the semi-major, semi-minor axis. Remember that stuff from math class? Chima's nodding his head. How about you, Andy? Remember semi-major, semi-minor axis? Good. Long time ago from a ellipses. Basically, a circle is just a special type of ellipse where the semi-major and the semi-minor axis are the same thing. I can do 30 versus 60. So we can create some really neat graphics things or whatever right there. So let me talk a little bit here. If you want, after my talk, maybe we'll take a 10-minute break and then we'll come back and let's just start the homework. So if that'll make life easier here. A lot of these things I already talked about, but I don't want to I want to make sure we're able to you figure out a method to my madness and where we're coming from with these programs here. How do we manage data? Because what we're going to be doing next week is doing the same exact stuff for Python, and our input parameters are going to be feature classes or texts or whatever we want to do, where we can add these up within the confines of our ArcGIS Pro software and automate some of those processes, because you already created some software related to that. And so when we start looking at our software here with our small basic, I conditions and loops, and we talked about a lot of these already. Most of you, if you notice, if you go to the down at the bottom, the small basic resources, a lot of those small basic resources have a link to like little tutorials, have a link to a PDF that have like little tutorials to go through and complete some of these programs. So thinking I'm smart and doing all this cool stuff, I'm just pulling from their stuff and then tweaking some of the things and doing whatever. So when we have conditions and loops, basically programs that carry out different instructions based on logical conditions. What were some of the logical conditions that we looked at? What did Chima do in his quadratic formula, or all of you do in that quadratic formula? What was the one condition that he set? Yeah, if statement. I better check that discriminant, because if it's less than 0, bad things are going to happen. If I do square roots of negative numbers, I'm going to have bad things happen. Then also I set up the scenario for a double root, but you don't necessarily need to. You just set up root 1, root 2. Also, what was the negative thing? Hey, keep going through and adding stuff in until you type in -1. What if you forgot that you had to type in -1? You're just going to be stuck in that program forever. So there's other ways that you can get those things out. Those are compound statements where we can do or statements or whatever as well. Or that for loop, for x equals 1 to 50. Keep going through until you get to 50. I just counted by 1, but you can count by whatever you want. So we can repeat instructions until a specific event occurs. Meaning you type in -1 and then we're out of there. You guess the correct number. Because with that loop or the -1 loop, you don't know how many times you're going to be in that loop. So a couple things that we can look at. This is very, very kind of fundamental. And the one thing that differentiates this from Python, from C, is the syntax. Even me, like learning this basic from when I learned basic when I was a kid, was even the instructions are a little bit different here. And so we have different programs. If clock day equals 1 and clock month equals 1, so we have a function here called clock. Okay, function called clock and day. We've looked at a couple of these functions. One's called math.square root, math.power, math.cosine. And if you notice for that guessing game, I had one called math.random. It just picked out a random number between 1 and 100. So I hopefully specified the numbers between 1 and 100. You can pick out random numbers in Excel. Have you ever done that before? I do this all the time for your classes when you need to do presentations in order. So I export everything to a spreadsheet. I put a random number next to your name and I just sort it, and then just all the names go in the random order based on the number you got assigned to. So we don't go in alphabetical order. It's truly random. And so text window.writeLine is Happy New Year. So there are these different objects out there. I guess the proper term would be objects out there. Okay. So the program instructs the computer to display Happy New Year only if today is January the 1st. So if clock.day equals 1 and clock.month equals 1. What's this word and mean? Exactly, both need to be true. Okay, and so this is what we call a logical intersection as opposed to a logical or. Because if we put the word or equal, or was here, it means it could either be the first of the month or it could be in January. One or the other. And so make sure we differentiate between and or, especially when we run in these logical errors a lot of times in our classes here. And so we have the if, then, and if. So the then is followed by the action. And I think in small basic, it indents it a little bit. When you start programming in Python, this indent is going to be really important where everything needs to be lined up within these if statements. Yes, really important. The other things that we've got here. Oh, excuse me. Some of these conditions here that we have. If the clock hour is less than 12, then did you have your breakfast? If it's greater than 12, did you have your lunch? What are these things asking? If it's morning, or if it's afternoon. Okay, pretty straightforward. And then we can kind of lean on you for the actual syntax. The main thing that I want us to worry about here is the logic. What are we doing? And more importantly, why? Okay. So depending upon when you run the program, we'll have different results. Did you have your breakfast? So these are what we call like system properties. So this is going to be pulling from the date and time in your actual computer system as opposed to some sort of user-defined input, whether it's a mouse click, a mouse down, or something that you type in. Did you have your lunch? And then we have some more commands here. If the clock hour is less than 12, did you have your breakfast? Then did you have your lunch? And if, okay. So repeats a lot of the information that we already have here. Okay, so we have if, then, and then we have if, then, else. And so what Chima ran for his program was he just did two separate if statements, right? I ran if else. Which one's right? Which one's more right? Neither one's right. I was going to say mine was, but either one would work because these things are going to be mutually, just like Chima said, less than 0 or greater than or equal to 0. They're mutually exclusive of each other, meaning it can't be, it's got to be one or the other. Or in my situation, it was one of 3 situations. It was 0, less than 0, or greater than 0. And so you can see here, these two things mean the same exact thing. I just did, this is done in 5 lines, this is done in 6 lines. Okay, but to me, this probably makes a little more sense that people are able to understand it. But once again, if it's going to run this, otherwise it's going to run this. The only possibilities is that it's less than 12, and then any other scenario from 12 to 24, or if hours go up to 1,000 or whatever they're looking at there. And so these are pretty much the same thing. And so we can enter a number, we can do a remainder, we can see if things are odd or things are even. I've done a couple of neat things before where we can look to see if things are prime numbers. Okay, prime numbers, because look what we have here. We have a function here called remainder. So what's the definition of a prime number? Prime number. Is 50 a prime number?
Divided by itself.
Divided by itself in 1. Yeah. So 2, 3, 4, 5, 7, 11. So somewhere in here, I've got some neat prime number calculations because we've got this function here called prime number. So we can just throw it into a loop and say, hey, type in a number. Is it prime? I want all the primes less than 10,000. I bet you during the break, I'll probably write a prime number generator for everyone and we can come back and look at it. That'd be pretty cool. I'm into prime numbers and Pythagorean triple, so. But we can also see if they're even or odd or divisible by certain numbers. But that gets a little weird here and there. So we can look at some of these conditions here. So if the remainder is equal to 0, then this. Otherwise, it's either even or odd. Those are the 2 possibilities that we have here. And so when you're writing a complex problem, you want to check whether it's even or odd. We can do that. We can use an if then else. I like the separate if statements just because you're really creating those separate if statements, and I think they're a little easier to understand, but either's fine here. The current temperature, it's warm today. Here's some more if then else statements here. where it just looks at temperatures, whether it's cool, warm, very cold, or whatever we're looking at. And so we've got some of these once again. We get a little bit more into loops. Basically, when we loop, we want to perform the same instruction because you're going to be making times tables for my kids where I want the 5 times tables and you're going to 5 times 1 equals 5, 5 times 2 equals 10, 5 times 3 equals 15. And so when we write those, we're going to write a for loop. So we can also use a while loop as well. And so while loop basically needs some condition to enter, where that the for loop, it's going to run as many times as we dictate. Maybe you can type in for x equals 1 to however many times you type in some variable. And so we've got some loop statements here as well. So we've got a couple of them here. The end for loop and the end for loop is the code that's specific. So we have for a equals 0 to 10, right line, and we get something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretty straightforward. Now think about this for that very first program, that model program that you wrote. Can you stick that into a loop? It really is. That's a great thesis. Great, maybe, yeah, that's a great thesis topic. Where you do the stuff from week 1, you throw it into a loop, but are we writing from 1 to 10? No, we're just writing from 1 to what? First file name, the second file name, the third file name, the fourth file name, and we're doing all the same stuff within that loop. And we can load in things called arrays, meaning instead of it being a number, we can load in the file name. So we can just pre-program those file names .txt, bring them all in, and just run that same exact model over and over again. Does it matter if we write the stuff over? I don't care. I definitely don't care. Okay, I just want right answers. And so we can start to run things like this: for a equals 1 to 10, right? A plus a number equals this. Okay? So we can start to kind of get a little more complex where, oh, we're doing multiplication tables here, right? So number equals 5. You can input the number too, like, hey, write a number for the times table. So I don't want 5, I want 16 or 23 or whatever we're going to do here for our times tables here. And so this, literally this, 5 lines of code, you can generate all this. And then we can do different steps right here, meaning instead of counting by 1s, we can count by 2s. So we can start at 1, go to 9. So we got 1, 3, 5, 7, 9. Count by a certain number as well. And so we can increase these, and then we can look at different conditions. So that's that while loop that we talked about before. So while a is less than 100, and then it's the same thing as a for loop, but we increment it. And so we looked at a couple of conditional statements where we ran things where it says, hey, keep running this thing until you type in -1. Keep running this thing until you type in the correct number. And I created some sort of flag or solved, I forget what it was, guess correct equals 1. Now the only way that it could be equal to 1 is if you guess the correct number. The only way you could stop averaging those exams is if you type -1. And so we can look at some of those escape characters or escape scenarios where we can do that. So we've got programs, we've got construction, we got these if statements. So what we're going to do here is we'll take a quick break here. Let's take about 10-minute break. We'll come back at like 6:17, 6:18, and then we'll just do the rest of the time working on the homework. We'll work on it together as well. So how's that sound? And I'm going to write a prime number generator while we're gone. So how's that sound? Is that fun? Oh, I would. No one's enthusiastic about that as me.
Exercise 3. Screen. When I got this one, yeah. So sorry. These are it's something. This is also something. This week's this. It's the same. And four cells. This part. First one really good. Start with first one. Third question. I think it's this.
I'll be back in a minute here.
The small business on that. Yeah, it's not so. Just small piece.
Yeah.
With here. But to get it installed on. This is.
Play the game basically, and like those resolutions stuck. So I figured it out, and I got 5 bags of chips in the place. Sorry about that, but you're in a rock. You're in a rock. That thing is heavy, it's so moving. But yeah.
Yeah, I'm right. Yes. Yeah. No, okay. Install it. I got a little password here. It's the same password we had installed. You got that password? Let's try installing it again. Next. Okay, types. Okay, so during the break, I wrote a little for loop and then we're gonna start talking about the homework. So if you want, let's open up that homework and then we'll start getting into that. But I wrote a little loop here that says, what we want to do here is we want to see if a number is a prime number or not. Now, if a number is a prime number, how many factors does it have? 2. One in itself. Good. And so you can start to see what I did here. I've got some loops here. So I just said, hey, user, type in the little number here. Type in the number that I want to see. 50, 33, whatever. And now I've got a loop here that says for x equals 1 to number. What's the number going to be? So I've got two variables here. I've got a variable here called number, and I got a variable here called x. Okay, and I want to make sure you understand the logic, the logic behind it here. Okay, so what's the number you're going to type in? What number are you going to type in, Barbara? 3. Let's get a bigger one. 103. Good. All right, 103. I want to see how the people get the idea of the loop here. So for x equals 1 to 103. So we're going to do this loop 103 times. And this said if math dot remainder number comma x equals 0. Okay, what is this comment? What does this mean right here? We look at this. Okay, let's break this down. Math dot remainder. What do you think math dot remainder is? It's a math function that will return the remainder of what? 2 numbers. The numerator, which is going to be the number, and x, which is going to be the denominator. So the first time I run the loop, this is my little for loop right here. X is going to be 1. Now, the first time I run it, is there going to be a remainder there? No. Okay, so the remainder is equal to 0. Okay, now if the remainder equals 0, it's going to say num roots equals num roots plus 1. That's basically we're counting up the number of roots. Is 1 going to be a root of 103? It better be, because 1's the root of everything. And so num roots equals num roots plus 100. Num roots equals num roots plus 100 plus 1. And so when I run this, we're going to type this in. Now the next time I go through, the number's still going to be 103. That's not changing. X in this loop is going to be 2. Is there going to be a remainder when we do 103 divided by 2? Yeah. All right. So are we going to increase the number of roots? No, it's still going to be at 1 root. And then next time we're going to do it is 103. X is going to be 3. Is there a remainder with 103 and 3? Yeah, I don't even know what it is. I don't care what it is, to be honest with you, right? I just know it's a remainder. But if we want to be technical, I think the remainder is going to be 1. Okay, and so the remainder is going to be equal to 1. Once again, it's not going to do it. 103. I know for a fact there's not going to be there will be a remainder here because this is an even number and odd, and I just unfortunately know that, and so forth and so on. And so we're going to go through and count it. So let's see, when we run this, let's see what Barbara has for us. Okay, the number has 2 factors. If it has 2 factors, the number is prime. So you picked out a prime number, didn't you? Okay. And so we're going to go all the way through every single number right here and count the number of factors. And so we're going to have a text window that says this number has blank factors. And it just says if number of the roots equals 2, because can a number have less than 2 roots or 2 factors? No, we're not going to deal with any of that in mind when we're garbage or anything like that. It's prime. Otherwise, the number is composite. Can a number have 3 factors, or does it have to always have an even number of factors? Ooh, I stumped a couple people. Get it? Let's try one. Let's run one. Let's run this one. It's got 3. Well, yeah, that's because it's a perfect square, or you're writing something like that. But that's pretty. Most of the time, it's going to have a lot. What are numbers that have a whole lot of factors? I think numbers like 48 or something like that. Got like 10 factors here or something like that. So we got a prime. It just calculates if it's a prime number or not. Now, when we start to get into big data and total number of calculations, when I do this for loop, and this is kind of just thinking big picture right here. When I do this for loop, how many different calculations is it going to do? 103. Okay, we can just set this number is equal to 103. Do I really need to do 103 calculations? No. How many do I really need to do? 2, a little more than 2. But this loop goes all the way up to 103. I don't necessarily need to go up to 103. I can go up to the square root, because if it's not divisible by, if 100 is not divisible by 25, then it's also going to be 4, right? So I really only need to go up to the square root of the number, because once I get to 10 for 100, I got to 20. Well, I already covered that with the 5 on my way up. So basically, if I'm doing 103 or 200, I only need to go up, and sometimes they do n over 2, because basically, can I have 103? Is it divisible by 51, 52, 53, 54? Why not? Because it's more than half, right? Once it gets more than half, it's done. And so some of these big calculations, because you notice, what was one of the problems with that Pythagorean triple calculator? That was only going up to 500. It was starting to choke pretty quickly because it's doing all those calculations. So as you can imagine, you could probably throw out a bunch of calculations that it doesn't need to do. Now this thing was really quick. This thing was really quick, but let me type in a really, really big number, like Got stuck. Okay, why? Because it's going through all these, all these calculations, 46 million or 46 billion or whatever that number is, instead of really, it could just go through the square root of that. Okay, or that number divided by 2. Let's do one that's not quite as silly. Let's go 1 million. 1, 1, 2, 3, 1, 2, 3. Even now, it's still taking a little bit of time to run through all that thing. And you can see that 1 million has exactly 49 factors. So it takes a little bit of time. And that once again has an odd number of factors because 1,000 times 1,000 is a million. So that's going to be a situation where we've got an odd number of factors because it's got that double factor, that double root sitting right there. All right, so let's look at the second homework. We'll kind of finish this up for the last couple hours and we should be good to go. No, I want to be out of here by like 7:05 if that's okay. So. And I think we're going to have more than enough stuff to do here. And so we've got exercise number 3. We're going to open this up and we're going to kind of play with these a little bit. But this will be due next week, same class time here. All right, what do I have to do? I have to learn how to do my own homework. Okay. So we're going to download the files here and let's see what I've got here stored for everyone. So this is week 3. Looks like a really small file here. Oh, cool. I got some circles, event handlers, draw circles, conditions and loop, Pythagorean triples. So it looks like I provided a bunch of like kind of extra problems here that I've kind of put into here. So if we look at this, you can see some of the draw circles. I created an executable of it. And that's a program that'll run, I guess, on a Windows. I assume it's just a Windows-based machine. But you can see some of these programs, the draw the circles, the event handler with the mouse down, and the Pythagorean triples that I've created right here. But when I open up exercise 3, we're going to start looking at some of these. Okay, cool. All right, let's see what we got here. All right, so next, we're going to write a program here that asks the user input and prints out the multiples. Okay, all right, cool. So I'm going to write out some little times tables for my kids here as they start to learn them. So we're going to write a short program that asks the user for one number as an input and prints out the multiples of that number up to 12. So you can customize the output however you like, as long as it's understandable to the lay user. So you can have these lining up or whatever, but I want some type of input. So instead of me typing in 6, I might want to type in 12 or 23 or 800 or -7 or whatever that go up to 12. Because remember in math class, didn't they always go up to like the 12s? You guys had to like memorize all that stuff. I probably went to school so long ago that probably went to a much different school than y'all. But we had to do all the times tables. You had to know like a 12 times 11 and all that other stuff. But what we're going to do for a particular number where you go down this particular rows, we're going to write a program that does that. Oh, look what I just did for number 2. Oh my gosh. I think I just did number 2 for everyone too, and I didn't even realize it. Forget about that. All right, because these other ones start to get a little trickier here. Number 3 and number 4. Ooh. And that Pythagorean triple kind of gets there. And then number 4. Oh, the guessing game. Cool. All right. Yes, you're going to do the guessing game, which I really like too. All right, cool. So, all right. So first thing, we write this program here. Okay. What's the first thing we do? I want to write a loop that goes up to a certain number. What do you need to do? You're writing a program. I want to do times tables. What do you need to do first? You're the programmer. Where am I going up to? What number? Set a limit. 12. Well, this thing here, number 1 says it goes up to 12 automatically. So we're going up to 12. But 12, am I going by 6s, 3s, 8s, 12, -3s? What's it going to be? What are you going to say?
I did something a little bit different. I did a P6.
Yep.
I did a, I explain this. I did another text window for them to enter the number that they want to multiply. it,
Yes.
And I assigned it as a variable equals the text number that they enter. That way I can have my 1 through 12 or 1 through 10.
Exactly.
And they give you 5, 6, 7, 8.
Exactly. So first thing we need to do, have someone type in a number. Hey, what do you want them? I want my kids to learn the threes today. So 1 times 3, 2 times 3, 3 times 3, 4. That's what you're talking about, right? So we gotta get some input. Now we already know how to get input, right? So get input. And we'll create a prompt using the right line. And then we will do a read number, right?
So I did.
Okay. I'm kind of asking here what the best way to do it is here. And you know what I already have here? I already have this text sitting right here. So guess what I'm going to do? I'm going to copy it and paste it. So I can highlight it, right mouse click, copy it, and paste it right into a new program right here. Okay. So don't feel ashamed or, feel ashamed about having not copying code. That's what we all do here. That's how I make a living. Okay. I just go use someone else's code or stuff that I've already done before, cater it to what I'm trying to do for this particular problem. So please type in a number. All right, so next, I'm just gonna do a nice little loop here, and I want it to look like that on the left. And so I'm gonna type in a loop, and it says for, what's the variable gonna be? Does it really matter? Probably not. It was kind of like that X example before, but I'm gonna say X equals 1, 2, what? How far up am I gonna count? 12, exactly. I want to go to 12, right? Now next, what am I going to do here? I'm just going to print up my little times table. So print, and this is where this output gets a little bit tricky. So I'm going to write, all right, the first number is going to be X plus, now I got to put it in the string. I got to put in a little X right here for the multiplication symbol, plus, what's after that? Number plus, because I want to see what this stuff is going to be. Sometimes these things are called literals, what they actually are going to look like. And then what am I going to write after that? Blank times blank equals what?
Your text. Your
Good. Product of, how do I write X times Y? X, little star, little number. Let's look right here. So I'm just going to count up to 12. And so think about what this is going to look like here. Okay. First time I go through the loop. So what's my number? Say it's 7. What's X? 1. Well, actually, I'll just go on this side here. And what's X? 1. So what am I going to write? I'm literally going to write whatever X is going to be, 1 with the little X sign times 7 equals whatever the product of that's going to be. And then next time I go through the loop, what's the value of 2? 2, I'll put it in quotes here, times 7. So literally, this is just a nice 5-line program that you ask for the number, read in the number, we do our little 12s times tables. Do they do 12s these days in class, and make it go higher? And I had to do 12s all the way up to 12 times 12. I didn't know those. My teachers beat me. I think they did. They still spanked in my school. They don't spank in schools these days? They did? A little bit in Louisiana, they do. What's that? The nuns? Yeah, I taught at a Catholic school. I saw a little bit of that from time to time in the 90s. Yeah. Okay. So, let's see what this looks like. We'll type in a number. I'll just put like 3. Are these answers right? You know, 3, 6, 9, 12, 15. There they are. Pretty straightforward. Okay, so we have 5 lines of code and we can print out literally 12. You know, I can run this again. You know, -1. I can go -234.62 if I really wanted to. There it is. And these numbers all should, you know, make sense here. There it is. So you can see these nice little timetables that we've created. So, because remember what you're doing, you are writing the program so the person can do this. So you want this to look nice and simple, not simple, but easy to understand. Even though the numbers I'm typing in probably aren't that way. Okay, so feel more than free to cater it however you like. Oh, okay, number 2. Yeah, I already did that. I want you to change the output. I also created a I counted the number of roots, so you don't necessarily have to count the number of roots. And so you can see the suggestion here that I set up something called a. Did I put flag here? No, I didn't. So you'll need some type of for or while loop right here. Yeah. Sometimes I set up the word flag, meaning, hey, if we found a root, because if I count from the number, if I count from 2 to the number -1, like 103, the number that Barbara pointed out, how many roots does 103 have that are between 2 and 102? 0. 0, right? Absolutely 0. Why? Because we started at 2 and then we ended at 103. So it doesn't count 1 and 103. So I can set up that loop instead of going from 1 to 103 or 1 to the number you type in, 2 to the number below that. If you have 0 roots, then guess what? We're going to do that. Or you could set up some type of flag. So meaning, let's go through the roots. Let's go through all 102 calculations, 103 calculations. Go through the square root number of calculations. Because if you type in that big number like 1,000,000, you're not doing 1,000,000 calculations. You're only doing 1,000 calculations. Because if you get to 1,000 and you don't have a root yet, then guess what? You're not getting a root after that. Okay, just like 100. Like if I get up to 10 and I don't have any roots, then you're not having anything. Well, you got the 20, but 20 and 5 are also a combination. 2 and 50 are also a combination, but you're going to hit that 2 with the 50. So you can kind of count those as the dividend quotients. So the root and then the quotient if you set those up. So you got to do a little bit of kind of extra thinking right there with that. But I'm open to anything right there. Yes.
What if you say, if a number is divisible by 2, no need to check the other even numbers?
Fine, yeah. You can do a while loop right there. Andy had a good question, meaning, hey, I went to see, I automatically typed in an odd number. I typed in an even number. So once I got to 2, I was done. So that's another thing that you can do with like a while loop. While some sort of flag is equal to 1, like I call it like found. Found equals 0, and then once you get in the loop, you run the loop while found equals 0, and then you say, hey, if 2 is a root, then found equals 1. I'm done. This number's composite. We're out of here. Okay? You just got to make sure you got a way to get out of the loop after, make sure you have a way to get out of the loop once you get to 103 or whatever that number is. That's the tricky part right there. So that while is a good idea to get out of that loop because you don't want to do all those calculations if you don't need to, because this is really easy. And so when we start getting with like some big data and data wrangling and all that other stuff, when we look at Dr. McGinn's voter database, and we're working like 7 million records, I don't have to do 7 million calculations. I'm not going to do them. So that's a good idea. So number 3. Okay. Okay, number 3. Write a program that asks the user for 3 values. Interest rate stored as a decimal. Okay, cool. Do we know how to do that calculation right there? Yeah, compound interest. Basically, it's just based on how did I get 105 after the first year? 105 is just 100 times 5% of this. What's 5% of this? 5%, 5%, 5%, right? So it's just 5% of the previous year. That's how compound interest works. And I just want to print it out for each year. So you're just going to write a loop for how big is your loop going to be? How many years are you going to compound it for? 5, 4, 87, 203, or whatever you want to do. This is your interest rate right here. Okay, make sure you put it as a decimal, and then we can just go and calculate it. I think we can do this, right? Because the next one, I already did those Pythagorean triples. I went through and calculated those. And so we've got this one to calculate, and then I think that's it here. Oh, okay. Oh, you only need to do one of the following. So the Pythagorean triples or the guessing game. Okay. So for number 3, for question number 4, you only need to do one of the following. So the Pythagorean triple. And I would like you to kind of give a little bit more thought to the Pythagorean triples, because I run them in what we call nested loops, basically loops inside of loops. Kind of what we're starting to think about right here, if I wanted to run this inside of a loop here, because most of these are just going to be regular loops here, okay? But with the Pythagorean triple, it gets a little tricky because, all right, now I want to look at combinations of 1, 1, 1. Does that work? Is 1 squared plus 1 squared equals 1 squared? No. All right, 1, 1, 2. 1, 1, 3, 1, 1, 4, 1, 1, 5. Can 1, 1, 5 really be a real side? Can I have sides of a triangle that are 1, 1, and 5? No, because the A and B need to be greater than C. And so you can set up some parameters right there to kind of look at the stipulations with that, kind of like we did with the square roots. Because I just kind of do these in maths, meaning I'll just look at every single combination and see if it works. But what happened to that Pythagorean triple when we started running it? So last couple minutes, I'll talk about that Pythagorean triple. So you kind of see some method behind my madness, but it looks like I kind of already ran it. So I don't know why I gave you the answer there, and I have this guessing game here too that hopefully, oops, maybe not. This is the guessing game that I did, but I'll leave that one here. All right, this is the Pythagorean triples. All right, cool. Look what I have here. I got C equals 2 to 500. A is equal to 1 to C. B is equal to 2 to A. Okay. So the Pythagorean triple one, I'll kind of show you the method behind my madness if I can think of what I did right here. And then we'll kind of go back here. So we've got A, B, and C. Okay. A, B, and C. And so C is going to go from 2 to 100. A is going to go to 1 to C. And then B is going to go to 1 to A. Why did I do that? I don't know why, but I think for A and B, the highest you can be is C. You can't have a hypotenuse that is, you can't have, what is a hypotenuse? And I use all these fancy words here. What's a hypotenuse? Longest side on a right triangle. It's got to be specific to right triangle. So the longest side on a right triangle. And so the highest that A and B can go up to is what C is, because C needs to be the longest. So when I look at C right here, C is equal to, let's just say it's 2 right here. And when I start this loop, hypotenuse equals math power C comma 2. What's that mean? What's power mean? I raise something to a power, what's it mean? Multiplying that number by itself. So C is equal to 2. Okay. Legs equals math power A comma two, B comma two. So now B, A and B are one. And what am I doing right here? It just says, hey, if the hypotenuse is equal to the legs. So the calculation for the legs is 1 squared plus 1 squared equals 2 squared, question mark. Is 1 squared plus 1 squared equal 2 squared? Nope. Okay, so what am I not going to do? I'm not going to write, here's a Pythagorean triple. And then I actually counted the number of triples while I was there. That's pretty neat. That was nice of me, I guess. Okay, and then next, what do? I increase B by 1. And so now I've got 1, 2, 2. And I do the same thing again. Okay, so is 1 squared plus 2 squared equal this 2 squared? Nope. Do it again. Now I increase it 2, 2, 2. Is 2 squared plus 2 squared equal to 2 squared? Nope. And then what do I do next? 3, 2, 2. Is 2 squared plus 2 squared equal to 3 squared? Nope. Is 2 squared plus 3 squared equal to 3 squared? You get the idea of what I'm doing here? So what I'm doing is looking at all combinations where hypotenuse is going to be the longest possible value. How many of these different combinations or permutations do we have there? This is what we get into something called discrete math or combinatrix. But how many different combinations do we have to go up to 500? Whole lot. Whole lot of these. Okay. So who wants to do all that? Not me. I just went and did it. Okay. Yes, I definitely went through and did it. Yeah, and somehow I bring in this since this it works. That's all I know. So I'm gonna leave it like that. So when I run something like this, instead of me going up to say 500, we'll just do a quick one right here. But we'll just do 100 here. There it is. So you can see there's 52 Pythagorean triples whose hypotenuse. And so basically what we're doing is we're plugging in all different permutations of A, B, and C. This is basically, we're doing something called like raw force. Basically, we're looking at all combinations. This is a very elegant program. And we're just looking at combinations. At some point in time, we've got 11, 60, 61. Now let's see if it works. And I bet you we did also 11, 60, or 12, 60, 61, 13, 60, 61, 14, 60, 61. But think about how many calculations we did right here. Probably million? I don't know. Lots of calculations right here to find all these. And so as you can imagine, if I were to change this number to 500, have I increased the number of calculations by 5? A lot more than that, because now I'm looking at, in addition to going all the way up to 500, I've also expanded it by a factor of to a power of 3, which is nasty, like 400 to like the third power. And so now I start running something up to like 1,000. Hypotenuse is equal to 1,000. Look what the computer did. The computer's going to get really mad at me. But now we're just looking at these combinations. How long do you think why is it taking so much longer to calculate all these as I go higher and higher? That one took a while. Why is it taking so much longer?
That's for each value of the hypotenuse, it has to start from 2.
It's got to start from 1 or whatever algorithm I use to, all right, I got to go 1, 2, 500, 2, 2, 500, 3, 2, 500, 4, 2, or whatever I had in that loop there. So how long do you think it's going to take to do this? Where that I'm just working with 1, 1, 2, 1, 2, 2, and then that A should also go back to 1 as well. So there's ways that I could probably slickly do this as well. So how much longer do you think it's gonna take to go up to 1,000?
Probably a little while.
We'll leave it here. I don't have anything else today, so. We wanna stick around or we good? All right, good. I saw Dolores, it's okay, I'm out of here, good.
So the assignment for the bachelor's people to be with a condition that doesn't allow it to run like yours.
That would be great. If you wanna tweak around that Pythagorean triple, I'd do that because. We're gonna sit here for a little while, watch go all the way through 1,000. 1,000. 1,000 really isn't all that much. When we talk about Pythagorean triples, especially, we're also compounding this because that multiple of 3, 4, 5, multiples of 5, 12, 13, multiples of 7, 24, 25, multiples of 7, 40, 41 are also gonna be part of this as we go up there, so. All right, but I'm about done here. This is gonna be the kind of last, we're gonna focus on small basic programming, and next week we're gonna get into Python. My version of Python, the stuff that I do with Python, which we're gonna be taking an input, little text boxes, and the following, we're gonna be interacting with the ArcGIS Pro software, and then after kind of the midterm or after the middle of the class, we're gonna circle back to that with things like data cleaning and metadata extraction, pulling from metadata or checking null values, replacing null values, where we go through and do this over and over and over again because we don't want to do it by hand. All right, so we have a good charge for this week. I think we got a couple programs with the compound interest stuff that I think we can take care of. Well, I'm excited, so I look forward to all the stuff that I'm gonna grade here. Kind of see how you approach it and how you kind of turn from the pointers and clickers to the problem solvers to figure out what other people want to do. All right, I'm done for today here, and we'll let us all go, and I can go home and pick up some pizza on the way home, so all that other good stuff, so. All right, all set here, doing good?
Yeah.
All right, cool. I will stop it here and I'll address any questions here.